Hello, I'm Hanno from Pipedrive, doing database engineering here, and today going to talk to you about how we use MySQL in Pipedrive and about one particular data sharding case that is something that we've been using for a long time. That's a way for us to deal with a lot of different customers, a lot of data, and to do it in well manageable and highly performing way. As a bit about the background, we have 3 different deployment models, how we use MySQL. One of the main use cases is master-slave clusters, where we store our customer data divided by schema. Basically, we create a different schema for each customer and have up to 1,000 customers per master-slave cluster pair. We also have some other minor use cases in MySQL for smaller services and for high availability, for things that really need the best availability we can provide. We use Galera cluster. So here are a couple of numbers about scale that we're talking about. We have about 300 master-slave cluster pairs running in 2 data centers and hosting 200,000 MySQL databases. Data volume itself is actually not very big. There are instances of MySQL running this 50 terabytes of data alone, but as our use case is such that we do a lot of different things, our customers can do a lot of different things with our application. Then this usage creates congestions that are maybe a bit different to ones that where you could store customers' data for 1 million customers, for example, in one single MySQL table. That would be that kind of use case, for example, where a lot of customers do same thing, is not perhaps best suited for this kind of widespread deployment model that we mostly use here. Some nice logos. One interesting thing to note about here is that how we manage those master-slave cluster pairs is we use Corosync and Pacemaker to keep track of the MySQL replication relationship. Corosync is basically taking care of the transport layer, and Pacemaker is promoting the slave to master as needed, and vice versa. So how we deploy hosts? We use Terraform to deploy MySQL clusters, and everything that goes on after the operating system has been spinned up and accessible. Then we use Chef to take over and install services and configure them afterwards. Why we use Terraform? I think one of the important points for us is that we can use it to deploy into various different environments. We mostly use OpenStack and also AWS. We can use the same code basically to deploy into different environments. And in case of disaster recovery scenario, for example, we can spin up the whole environment in AWS and use the exact same code as we use for everyday deployments in OpenStack. One of the interesting challenges that came up with big Terraform projects is that Terraform creates a lot of objects. Every different thing that that you provision every IP address, every server, every disk, everything is a Terraform object. And if you want to deploy a lot of servers, then you have a very big Terraform state. And how you can make this a bit more manageable is to split it up into different projects. However, Terraform is a bit different from traditional programming languages, maybe, where you can just include submodules and so on. So there's this nice little hack that you can actually share code between Terraform projects and use symlinks to point to various objects. And so we have done this kind of a logical split up where we have like 10 project folders, and they're mostly using shared resources, but states are kept separately. So whenever we want to change something or add a new server, then Terraform doesn't need to refresh the whole big state with thousands of objects, and we can just keep the runs to a minimum. About how we are sharding customer data. When you have one schema per customer, then there is a need for some central repository or some place to keep track of where your customer's data is located in. We have used previously approach where we have created a Galera cluster that spans 2 of our data centers that has some nodes in our European data center and some nodes in US, and the multi-master cluster stays in sync over the ocean. It's not the ideal use case, but when used for a really, really small set of data, it actually works pretty well. However, it's still a bottleneck, and a single point of failure should the whole cluster fail, then both of the locations cannot serve data properly. So to mitigate this, we have switched this multi-master Galera cluster to different data synchronization mechanism, and we're using Debezium to connect to MySQL binlog and Kafka to sync events, and populate the directory of where our customer's data is located this way. So we can decouple the data centers and run them completely independently. Also, there's some tooling to take into consideration when you want to build such a system where your application controls where the customer data is going to be located, and also you have to upkeep all those thousands of schemas. There are a couple of out-of-box tools as well, but I guess it's the same reason why somebody won't trust their databases to Kubernetes, then we don't trust our 200,000 databases to Liquibase or FlyDB or a tool like that. It could work, but it can be a little bit dangerous. That's why to deploy changes to all of our database schemas, we have deployed in-house tooling called Alter Engine. That's basically a pretty simple tool. You take a list of all those databases, take a SQL that you want to run, and execute it in each and every one. When running something in 100,000 databases at once, for example, then some considerations need to be taken into account. For example, if you are going to alter a really huge table, then probably it's not a good idea to do it all at once in all of your databases. Also, the ability to control where the customer data is stored is pretty important, because some customers want their data to be in Europe, and some want the data to be in US, and in the future there will be a couple of additional locations even. So so to serve this need, we have built a service called Migrator, which is extracting customer data and importing it back into into the other location, and while updating the directory where the data is actually located in. The directory is basically a simple few column table that contains the customer identifier and then the pointer to a location where the data can be found from. This is kind of a basic service discovery mechanism. And from the logical picture how all of this plays together, there is also one more important component that takes care of managing the life cycle of database schemas. Basically, it will create some pool of pre-generated customer environments as a MySQL schema, and also maintain the lifecycle so that ones that are no longer needed are disposed, backed up, and removed from server. This data sharding approach is pretty expensive in terms of footprint. It will take a lot of resources to spread out on so large scale. So it needs to be thoroughly considered if the business case is supporting it. But it gives also a lot of flexibility. There is always a limited impact if something bad is happening in the database environment, then you only affect a very, very small subset of your customers instead of having to deal with the full outage. Why we have chosen the tools that we use, I guess we try to be as universal as possible and not to be tied into a particular vendor or particular environment. So things that work across the board are definitely ones that spark our interest most. I would gladly answer some questions if you have.
Thank you for your presentation. You mentioned 1,000 schemas per cluster. Why you choose 1,000? Do you have any problems with in the DB cache or with the logs?
Yes. But basically, I think we have reached this number by trial of error pretty much, and considerations are just what you mentioned. Basically, crash recovery, backup restore, and overall performance as well. We have concluded that when we put 1,000 customers into one server, then they pretty much even out the loads. If it would be less, of course, then hardware footprint would be even bigger. So we have to find kind of a fine balance somewhere, and also backup and all the rest. Creating a schema is also creating files in the file system. So it depends on how large the schemas grow. We have like 100 and something tables, for example, per one schema. So this gives already a pretty high number of file system objects, and we have seen that if we grow this couple of times that, then we already begin to have some issues. So that's how we reached this point. If you have much smaller schemas, for example, then you can, of course, do it a bit differently. So it's some trial and error.
Okay, thank you.
So my question is, how do you deal with online schema changes in case of well, quite large tables and so on? How do you keep your service online in that case? Because that's quite tricky, I guess.
You're right, it is tricky. One of the merits of this architecture is that the schema change only affects one single customer. So the rest of those hundreds of thousands of users are not affected. And when this particular customer's data set grows too big, then yes, this is a limitation, and this is a serious limitation actually of this kind of architecture. That when one single customer grows too big, then you're kind of out of options a bit. But yeah, to answer your questions, we just limit the impact to a minimum number of customers.
For some small number of customers, there's still some short downtime or something like that? Or?
Yes, there is.
Okay.
There's another question there in the back. Oh, almost. And someone passed it in the back.
Thank you. You showed very nice schema. Thank you. Very nice picture. So I was inspired to ask such kind of question. Which kind of modeling language is used inside of your company? I mean, UML or something different to communicate architecture, any changes? Who speaks this language in your company?
I have to say that it's kind of a collaborative process, and there is no strict formal rules what can and cannot be done. There is usually pretty well defined group of people working on one single particular feature, and yeah, there is no such formal frame to adhere to.
Thanks.
How do you handle schema changes or like rollbacks?
We don't do that.
But what if something goes wrong? You
Yeah.
have to revert an API and you have to revert the database as well?
Yes, it's a good question. We basically create a rollback change that is a reversal of the change applied previously. So we don't do like a rollback in a classical sense.
Okay, just another schema change.
Exactly. Yes.
Okay.
Exactly.
Makes sense.
I have this more noobish question just to sum things up. Can you maybe one more time explain why have you chosen this architecture over more simple one? Because it sounds like a lot of complexity and benefits of it are vague, or at least for my ear.
The main reason is to distribute the loads more evenly across our whole infrastructure. For example, if we would put everything into one single schema or several single schemas, basically, but all the customers' data into a same pot, sort of say, then we would create a lot of hotspots where we have really huge tables, and these would become quite nightmarish to maintain. For example, if we want to do schema changes, then doing it on 100,000 times or 200,000 times smaller scale is much more faster, and also recovering from errors is a lot easier. This kind of 50 terabyte database would require, I imagine, a lot of Oracle licenses.
So it's more comfortable to work, and it is more secure from this maintenance perspective.
Yes, it severely lessens the impact when some incident should hit, and also makes it easier to deploy changes and faster, and reduces downtime for customers as well. And also it makes it more universal. For example, more universal to move the data around. When you have to take one customer's data, for example, move it from US to EU, then you have a possibility to just export MySQL schema and import it in the other database, and it's done. When you have to do it from from one big shared database, then this creates a whole bunch of issues. If you have to extract a large amount of data and insert it back into another database, then and still you would have to have a similar kind of division, because if you want to run operations from multiple places, then you would have to have this kind of division anyway.
Thank you.
But it's by no means a perfect way, and how we have reached this point is again a result of evolution, and due to probably due to luck, because 10 years ago hardware was much more expensive and resources were more scarce. So this kind of sharding was much more important. Today maybe we would be in the situation where everything would be in one large pot and the machine would be huge, and then there is a ceiling, cannot get any bigger. So yeah, it's kind of evolutionary.
All right. One more question, then the next one maybe you can ask afterwards, because we're a little bit over time. So.
Hi, thank you for the presentation. It's really interesting. My question is, why MySQL? You have a lot of different, like MongoDB, Postgres, Microsoft Access. Thank you.
It's again initial choice done by our founding fathers, and it's basically made because at the time everybody who was developing our service, they were familiar with it, and also they were confident that today's and perhaps tomorrow's needs are met by MySQL. So that's why it was chosen. I'm pretty sure Postgres would work exactly the same, and all the rest as well, except Access. Thank you.
I have a small gift for you as well.